In this video of Chapter 5 in the periodic table, we're going to see a pattern of ionic charges on the periodic table. But before we see the pattern, we have to understand what ionic charges are and how we can predict them using electron configurations. So in this slide is the definition of ions. So when we talk about an ion is a charged particle, okay? So it's charged, and I'm saying particle because it could be an atom or a group of atoms. And when we talk about charge, it's important to remember that charge can be positive or negative. So ions are atoms or groups of atoms that have a positive or a negative charge. And how they get the positive or negative charge is by gaining or losing electrons. And so let's look at that. So first we're going to look at the positively charged. I'm going to underline instead of highlight because the red doesn't do well. So we call positively charged ions cations. Some people say cations. Either way is okay. Now I associate cations with Ca, and then the T in the middle makes me think of a plus sign. So I kind of think of that as the cation that T makes me think of a plus sign, like a mathematical plus sign. I have a funny story, or I think a cute story. Maybe it's just me looking back on things. But I had a student that came to me and was learning this. And she said, oh, I remember cations because cats have paws. And so they're positively charged. So that's how she remembered that cations were positively charged. And she had a real cute thing for the anions, but I don't remember it. It wasn't cute as cats with paws. So anyway, cations are positive charge. And here's something that's easy to get flipped around. When you lose electrons, positive charged ions are formed. Okay, so that is something you have to think. Losing electrons forms a cation. Now, below are some examples of how they're going to be written, and we're going to talk more. Really, at this point, it's just to see how they're written. We write the charges as superscripts. We put the number, if the charge has a number, we put it before the plus or minus sign. If there's no number, if the number's if there's not a number written, then the number is 1. And so just take a look at those examples so you can become familiar with how we will see them. We are going to learn how to predict ones like calcium, and the ammonium ion, which is polyatomic, will come when we're working on some of our naming. And I think maybe in Chapter 12. Now the other type, since there's positive and negative, so the other type is a negative charge. It's negatively charged. It's called an anion, and I always think A, and then that N to me stands for negative. So I think A, negative ion. So the N I just see as telling me that it's negative, and the T I see as a plus sign for a cation telling me it's positive. Now these are formed by gaining electrons. Now, I would ask you then, electrons are negative charge, right? Electrons have negative charge. And protons are plus 1. In an atom, the electrons and the protons are equal, so there's no charge. So the only thing we can change, we cannot change protons. If you recall, protons are what gives identity to the atom. So these are not changing for ions. They have to stay the same, not the charge, but the protons. And so then what happens with ions is electrons can be gained or lost. So now remember, they're negative charge. So if you lose negative charge, it means you'll have more protons now because they start out equal than electrons, and protons are positive. So when you lose electrons, the overall impact is you create an ion that has positive charge. When you gain electrons, electrons are negative. So if I take something that's neutral and I add more electrons to it, then it's going to get more negative charge. So adding electrons is negative. And again, I think this is easy to flip in our minds because a lot of us associate gaining things as being positive and losing things as negative. But what you have to remember is what we're gaining and losing is negative. So if you lose negative, that's positive. If you gain negative, that's negative. So practice with yourself getting those two things straight. Now, how we predict, we're going to predict how many electrons elements will gain or lose. And we use a rule called the octet rule. And so here you can see it. You can just read the octet rule right here. It just says elements will lose, gain, or share. And we're not talking about sharing now. We're talking about losing and gaining. They'll lose, gain, or share valence electrons to reach the electron configuration of the noble gas closest to them on the periodic table. So my question would be, why a noble gas? And the reason the noble gas is very stable. Remember, 8 valence electrons are the maximum. Like you can't go over that. And so what it is its outer shell where the valence electrons are is full. And it's 8 electrons except for helium, and helium's full at 2 because it doesn't have space for the p electrons. So the noble gases are very stable. They don't really want to lose or gain anything. Like they have it going on. And all the other elements want that stability too. So they will, of their valence electrons, not the core, not the ones below the valence, but of the valence electrons, they will gain or lose those to get to the number 8. Okay, so that's how we're going to predict. And I have a couple examples where we'll look at electron configurations to see what that octet rule is saying. But ultimately, what we're going to do is find a pattern, and that pattern is related to the periodic table, and we're going to use that pattern so that we can predict what charges our representative elements will form. Okay, so that's our goal. So before we get to that, just so you're sure, just so you can kind of see what I'm talking about, this says, what noble gas has the same electron configuration? And this word isoelectronic means same electron configuration with the following ions. So the first one, what I'll do is I look at oxygen, and when we actually call negative ions, we change their names. And we change the ending to IDE. So this is called oxide. The atom is just called oxygen. But when it becomes a negative ion or an anion, we change the ending to IDE. Well, oxide is 2 negative, so it has gained 2 electrons. So if here is oxygen and it gains 1, 2, then it would have the same electron configuration as neon. Now it is not neon because the identity of the atom is determined by the number of protons. That's not changing. It is oxygen that has gained 2 electrons, so it's called oxide. Now, magnesium is right here. It has a 2 plus, which means it loses 2 electrons. Now, as far as calling the ions their correct names, The positive ions, the cations, they don't change the name. So you have a magnesium atom, and then we just call its ion a magnesium ion. So magnesium is right here. And what we're saying is it loses 2. So it loses 1. And then to lose the other one, it has to come back to here. And so this one also looks like neon. So all 3 of these, oxide, magnesium ion, and neon, are actually isoelectronic because they all have the same configuration as neon. And now finally we have Br, and it's really hard to see here, but there's a -1. And so it gains 1 electron. Now, Br would be bromine. Br negative is bromide ion. So as we start to use the correct language with these ions, the anions change the ending of the element to IDE. So that's bromide. So it's gained 1 electron. So I find bromine here, and it gained 1 electron, so it would have the same electrons as krypton, which is Kr. So this is what the octet rule is telling us, that for ions in the representative elements, to be stable, they either gain or lose so that they can have the electron configuration that is like one of these over here in the noble gases. And again, those are very stable because they have a complete valence shell. Okay, so let's see the pattern of this. Now, what I wanted to do was show you with just 2 groups how we can visually see the octet rule by looking at electron configurations. Now, electron configurations were discussed in detail in Chapter 4. We have used them also some in Chapter 5. I am not going over how they're written here. If you need help with that, go back to Chapter 4. You can ask me questions. You can ask tutors questions. So this, I'm just looking at them. So let's see. I have the element sodium. Oops, I got to change. So the element sodium, and sodium is right here. It's atomic number of 11, and that's its electron configuration. Now the closest noble gas to sodium is actually in the previous period, and the closest one is neon. Now this is what I want you to see. If I take away, now watch on the video, I'm taking it away. If I take away that 1 valence electron, sodium has 1 valence electron, and now I've erased it with my pen. And now I want you to look, when I erase it with my pen, sodium and neon have the same electron configuration. That's the octet rule. Right? The octet rule says that the element sodium will gain or lose electrons to look like the noble gas that's closest to them. So what sodium does is it loses that electron. And see, you can see it when I write it over. So I'm going to write, this 1 electron, it's going to lose it. And when it loses 1 electron, it becomes a +1 charge. So it becomes Na with a +1. And the cations are named the same as the element. So this is a sodium ion. Now here's the really great thing, and this is what I want us to think. It's a pattern. So every single atom in this row, all of these have 1 valence electron. And so all of them will lose that 1 valence electron to be like the noble gas that's over here. So what we can do is we can predict, okay, sure, sodium's a +1, but so must potassium and lithium, that everybody in this column we're going to predict is a 1+ ion. And I'm writing the 1 there just because it's easier to see and just not having a plus. But when we write the formulas, we just write the plus. So now let's look at the group next to it. Let's look at magnesium. So if you look here at the formula for magnesium, right here, there's its electron configuration. And here it is on the periodic table. And like sodium, the closest noble gas, you would go backwards to go to neon. So let me again just scribble out. So magnesium has 2 s electrons in its outer, and I'm erasing them right now. And if I take out the 3s2 and I've erased it, you can see that it looks just like neon. So bring it back. I'm going to erase it again. Look again. So it's like neon. And so that is what magnesium does. Magnesium loses these 2 electrons. When an atom loses 2 electrons, it has a 2+ charge. So magnesium has a 2+ charge, and cations are named the same as the element. Now again, what I find really cool, I love patterns on the periodic table. Everybody here has 2 valence electrons. And so what we predict is that all of those will, to follow the octet rule, will all follow a 2+. Now if you recall, here is the stair-step line, and the elements to this side of that line are metals. And what we see is metals will go backwards. They'll go to the previous row to get to the noble gas closest to them. So we can make a generalization that says I didn't mean to do that. Metals lose electrons. Okay, so that's one thing I want us to remember is metals form cations. Okay, that's an important generalization. And so what I really could tell you is even if I come over here, now we're doing the representative elements, which is all the tall groups, that the pattern would continue. These are not part of the representative. The pattern would continue to 3 over here to 3. Just like I was doing. I'm not writing all the electron configurations, but it would continue. So now let's take a look at the anions. Let's take a look at the other side of the periodic table. So here we're looking at group 6A. And I want you to look at oxygen. And compare, here's oxygen. And again, oxygen, the closest noble gas would be right here. It's closer now. We're farther to the right, and so we're moving toward the noble gases, so it will go toward the noble gas. And so to get to that noble gas, oxygen would have to gain 2 electrons. Now, if you compare these two, if I look at oxygen, it has 4 in its P. If I added 2, that would be 6. And so then if I change that to 6, I now see that that would look the same as neon, right? It has 4, but if I add 2 more, it's going to have 6. So that is what it does. It gains 2 electrons, and so that means oxygen becomes an oxide ion with a 2 negative charge. Now remember, the negative ions change their name. They take what they call the stem or the beginning of the element name, but they change the ending to IDE, or what we say IDE. And so I can make a big generalization and say, okay, all of these here have 4 valence electrons. Sorry, my tongue was tied. And so they will all gain 2. So this column likes to have 2 negative. So I could predict sulfur would have a 2 negative. Like anybody in that column, I predict 2 negative. And let's go now to the next one, fluorine. So here's fluorine. And I look down here on my electron configuration. I see that fluorine has 5 in its p sublevel. Well, the closest one is neon, and it has 6. So if I change the 5 to a 6, it looks the same. So that's what it does. And so since fluorine gains 1 electron, it's F with a -1, and they don't write the 1, they just write the negative. And you think in your head, what do you think we changed the name to? Fluorine becomes fluoride. And so then again, we think to ourselves, okay, all of the halogens, everybody in group 7A has 7 valence electrons, and to get to the closest noble gas, they would just have to gain 1. So then we predict that the halogens all have a -1. So let's make a big scheme. So I went over 2 using valence electrons. Oh, wait. Back up. I'm sorry. I want to highlight this, that nonmetals gain electrons to form anions. So like metals form cations, nonmetals form anions. Okay. All right, so now what I want to do, okay, now I have to get my train of thought where I was trying to lead you. So I did 2 with electron configurations for cations and 2 with anions. And we don't have to always do electron configurations. What I just want you to see, why I do it, is because I want you to see when the octet rule says, oh, look like a noble gas, I want you to see, we can understand that. Like you have enough knowledge to see what that means, looks like a electron configuration of a noble gas. But practically, we want to be able just to have a pattern that when we quickly need an ion, we can just refer to the periodic table. So let's get that pattern. We've already started it. And I'll come back to this in a second. Okay, I can draw the pattern on this one. Let me go back. I hate to go too out of order. Sorry for any kind of back and forth on the video. So your book tries to generalize it one way, and that's why I included this slide. It just says the charge of an ion from a metallic representative element. Remember what they're talking about is these are metals and these are nonmetals, and I can't write nonmetals without I'm going to go off the page. So it's saying the metal is equal to the group number. And they're talking about representative elements, so they're only talking about the tall ones. So that would be a 1 plus, 2 plus, 3 plus. And then it says the charge of an ion from a nonmetallic representative is determined as follow. You take the family number and you subtract 8. Okay, so the family number, they're talking about the number in front of the A's. So 5A would be a 3 negative, 6A would be a 2 negative, and 7A would be a 1 negative. The noble gases are a 0. Now, the middle column, the 4, they're in the middle. They have some metals and some nonmetals. So if I was using what they are predicting with this, I would say a 4 plus would be for my metals and a 4 negative would be for my nonmetals. But in full disclosure, the 4 negative for the nonmetals does not happen. It's too big. The nonmetals up at the top, if you remember the trend, the smallest atoms are in the upper right, and the nonmetals are too small. The 4 negative charge is not very stable. So students never like that. And some books, just because it's like, well, this is what we'd predict, but it doesn't really happen. I like to keep it on my pattern. Some books just leave that 4 off. They don't put it on there. Now, so your book is really trying to go back to the numbers on top, which I appreciate, except what I want you to know, remember, we already predicted 1 plus and 2 plus based on electron configurations, and then we predicted 2 negative and 2 minus based on electron configurations. Since the group numbers are related to the valence electrons, you can think about those when you're making the trend. Okay, so on the next slide, I'm going to show you, we kind of like think, how do they make ions? What's the octet rule? This is our pattern. Like, how would I use this? Like, it's a lot to process, but we need, like, how am I going to use it? So what you're going to do is, this says write the formulas predicted by the octet rule for the following elements. And I really should say the formulas of they would probably call them stable ions, but the ions. Like, we're predicting what would be stable. Okay. And to predict that, to answer this question, you memorize this pattern. It's a 1 plus, a 2 plus. Now, we're not predicting these. 3 plus, 4 plus, 4 minus, 3 minus, 2 minus, 1 minus, 0. This is our pattern. That is the charge for these groups. Remember, the periodic trend, which is that elements in the same group have similar chemical properties. It's all based on their valence electrons. Elements in the same group have the same valence electrons, and that's why they have similar chemical properties. So we're using these valence electrons to predict a lot, including the charges. One thing I'm very pattern oriented, and I don't know why. I was thinking across the periodic table, and it helps me just to think as I go across that, and then that has 0. I'm like going up. So I start at 1, and then I get bigger, and I get bigger. And when I get to the top, this is my turning point, and then I go back down. And so however you're remembering this pattern, it doesn't matter. Remember this pattern, okay? I've tried to, in this video, explain to you how we get the pattern using the electron configurations, but we want to remember this pattern to answer these questions. So this is what we're going to do. We're going to answer the question. And you can pause now and see if you can get it, but I'm going to go through each one. But pause at any point to see if you can figure out the answers. So for letter A, calcium, I go to calcium, and then I see it's a 2 plus. So calcium is a 2 plus. That is the calcium ion. I can't write it down because I don't have enough room. Okay, then I go to Se. Se is over here. It's a 2 minus. So it's Se2 negative. I'm going to write this name down. Selenide ion. So it's a negative. I'll write calcium up here. Just to practice the naming. We need to get the language down too. But it's a negative ion, so they changed the ending to IDE of selenium. Okay, potassium, right there. I look up here, it's a 1 plus. And it's not going to change, like that's what it is. Positive ions are named the same as the element. Bromine. All the halogens are negative 1. And then then aluminum. 3 plus. And it would be called aluminum ion because it's a positive. Don't change the name. So what you're trying to do is predict charges. We're going to need to know what the charges, the representative elements form, for things we're doing with bonding. And we don't have to memorize all the ions. What we're going to learn is the pattern that the periodic table is predicted on the periodic table that we can learn. Let me say one other thing for the 4. So these are the 2 elements right here that we might see with 4s, tin and lead. So that's not uncommon. And we'll get to it. I just want you to be exposed to it. So this is it for this is it for the ions in chapter 5. We'll be using this again, so just practice. And as always, feel free to ask questions.